So what is reaction quotient? Reaction quotient is the ratio of concentration of products divided by concentration of reactants. Always, it is written same as equilibrium constant. So what is the difference? The difference is that reaction quotient is a general ratio. It could be at the beginning of reaction, or at towards the end of reaction, or at equilibrium of reaction, near the equilibrium of reaction. Anytime if you derive the ratio of concentration of products divided by concentration of reactants raised to the power of their coefficient, this ratio is always known as reaction quotient. When this reaction quotient is at equilibrium, then this reaction quotient is known as equilibrium constant. So equilibrium constant is equals to reaction quotient at equilibrium. Let me tell you some more application of reaction quotient. How it is written? It is written same as equilibrium constant. All right. So same way as for reaction A plus B gives you C plus D. If you would have written equilibrium constant, how you will write? Concentration of C into concentration of D divided by concentration of A into concentration of V. Now, what is the use of reaction quotient then? So let me tell you, if Q is if Q is reaction quotient and its value is lesser than equilibrium constant, its value is lesser than equilibrium constant, something like this, Q is less than Kc, then that means reaction has not reached equilibrium. So it is going still towards forward direction. Reaction is moving in forward direction. If reaction quotient Q is less than Kc, we have taken this condition already. So we'll take another condition as Q greater than Kc. So that means reaction has moved ahead of equilibrium. The sole purpose of equilibrium is that each reaction wants to be at equilibrium. Equilibrium is the condition of comfort. So every reaction which is reversible wants to reach at equilibrium. If you disturb the equilibrium, it will again do whatever needed to come back to equilibrium condition. So initially, if reaction is beginning, it wants to reach at equilibrium, reaction is moving forward. If for some reason you have added some reactants or you have added the products, so reaction has moved ahead, so it will come back to the equilibrium. So whatever is needed it will do, and it will wants to stay at equilibrium. So if at a point, if reaction quotient is greater than Kc, then reaction is moving backward. And if Q equals to Kc, that means reaction quotient equals to equilibrium constant, that means we are at equilibrium. Reaction is at equilibrium, right? So Kc is a constant value. It is depending on temperature. For a given reaction, Kc is constant, and Q depends on which stage of equilibrium we are at, or which stage reaction is at. So if it is beginning, then Q is very less. So it is proceeding towards equilibrium. So reaction is forward. If Q is greater than Kc, that means it is proceeding backwards. If Q equals to Kc, that means reaction is at equilibrium. So by comparing Q and Kc, we can predict the direction of a reaction at any particular time. Alright. So this is the application of reaction quotient in comparison to equilibrium constant. Now few more relations you have over here. We have Gibbs energy change delta G, and we have another value at a standard condition delta G naught. So delta G naught is at standard conditions. What are the standard conditions? Temperature is 25 degrees Celsius. Pressure is 1 bar. So these are standard conditions. Alright. So delta G at these values is known as delta G naught. Similarly, delta S naught is at standard conditions. So what is the relation between delta G naught and delta S naught? Is delta G naught equals to delta H naught minus T delta S naught. Right? What is delta G? Gibbs free energy change, delta H enthalpy change, and delta S entropy change. If naught is mentioned like something like this small zero, right? This we call that as naught, and this represents delta G is at normal conditions and delta G naught is at standard conditions, right? So what is the relation? Delta G naught equals to minus 2.303 RT log Kc, and if you want to compare for Kp, you have the same relation, delta G naught equals to minus 2.303 RT log Kp, right? If we were using natural log, then you will say minus RT ln K, right? Delta G naught equals to minus RT ln K. And you have few relations over here. If delta G naught is less than 0, that means it is a spontaneous process, and if Kc is greater than 1. If delta G naught is negative, Kc is greater than 1. If delta G naught is positive, that means non-spontaneous process, then Kc is less than 1. If delta G naught is proceeding, if somebody asks you whether a reaction is spontaneous or not, what you will say? You will see if delta G naught is negative or positive. If delta G naught is negative, that means reaction is feasible, possible. If delta G naught is positive, that means reaction is not possible. Alright. So delta G naught tells us whether a reaction is possible or not possible. Spontaneous means possible, non-spontaneous means not possible. So we have few values. If delta G is less than 0, that means a spontaneous process, a reaction is possible. If delta G is greater than 0, that means non-spontaneous, non-spontaneous. And if delta G equals to 0, that means equilibrium. This means equilibrium. Alright. So from here you can compare which process is currently going on by seeing at the value of delta G. At equilibrium, delta G is 0 and delta G naught equals to minus RT ln K, right? And if you have log, you will say 2.303 RT log K. K means Kc or Kp, depending on, this is at equilibrium condition. Alright. So this is all we have to discuss right now.